And okay, so a pleasure to have Gemma again for the second lecture. Please, Gemma, the floor is yours.
Thank you very much, Stefanella. So we're going to continue with this mini course on mathematical neuroscience. And today what I want to do is I want to talk about excitability and oscillations that appear in the models for single cell. That is for models for the activity of a neuron. To start, let me recap you what was the program for this mini course. So in the previous session, I explained you a little bit about the membrane biophysics for the cell, for the neuron, and a very classical model that constitutes the paradigm to describe or to design any model, for spiking neuron. And today what I want to do is I want to analyze this model and tell you about what is the output of this model. So, and what type of properties do they have? And to do that, what I'm going to do is I'm going to make a reduction to 2 dimensions. So this is the goal for today. And remember that for the sessions next week, I'm going to talk about networks. So for today and previous session, we're going to be talking about models for a neuron. And then next week, we're going to move to networks or like populations of like thousands of neurons. Something that I forgot to say in the previous session, so I put it here at the beginning for this one so that not to forget, is that some references, some list of references. Basically, what I'm explaining and some of the pictures actually are taken from these 2 books, one by Bart Ehrmantraut and David Terman, Mathematical Foundations of Neuroscience, and another one by Ezekiewicz. The first one is more oriented towards mathematicians, but the second one is, I think it's a very nice book for people who are not into dynamical systems and they want to learn a little bit about it. So it provides like very nice introductory chapters. And there are also other books, the one by Kinner Sneed or Stephen Strogan. So that some parts I'm going to use from them, but the ones I use the most are the references number 1 and number 2. So back to the topic for today. So excitability properties and oscillations. So let me say that we're going to start from where we left in the previous session. So in the previous session, I talked about the neuron. I mentioned that the experimentalists, what they can register or record from a neuron is the voltage, which is the membrane or the membrane potential, the difference between the interior and the exterior of the cell. And that typically this type of voltage traces show these spikes or these peaks that when we zoom in, they have this shape that is shown here in red, and they are called action potentials. And actually when a neuron is showing a train of these spikes, we say that the neuron is active. And we presented a classical model designed by Hudson and Huxley in 1952 to describe the evolution of the voltage of a neuron. And this classical model consists of a set of 4 differential equations that involve 4 variables. One is the voltage, which is the variable that we have access to and that the experimenters can record. And actually, the voltage is governed, or what affects the voltage are changes in or movement of ions across the membrane. And this movement of ions occurs through channels that are ionic, that are specific for each ion. So they are selective for ions. And I basically talk about 2 important ionic channels, the sodium channels and the potassium channels, that we modeled as using the current, using the Ohm's law, which is basically a product of a conductance times the voltage. So the sodium channel, which is modeled, the sodium current, sorry, which is modeled as the product of a conductance times a voltage. And what I explained in the previous session is that these channels may open or close. And we have these three other variables, M, H, and N, which are called gating variables, that they have also its own dynamics. So they have a differential equation to describe their evolution, and that they basically control whether these channels are open or closed. And actually, the voltage, so the fact that these channels open or close depending on the values of the voltage. So they are voltage dependent, okay? And basically what happens is that typically a neuron, when it is at the resting state, these sodium and potassium channels are closed, and we only have a leak term, which is here. But then if due to a brief perturbation, this causes the opening of sodium channels, then, is there a question?
No, there was no question.
Okay. This causes these channels to open, and when then sodium flows in, and it causes a depolarization, and it's very rapid actually, because the opening of these channels is quite fast. So this, the dynamics for this variable M, which controls the opening of the sodium channels, is fast. And then soon after, what happens is that the potassium channels open, then potassium flows out, and this causes the voltage or the membrane potential to repolarize again. Okay, so this brings back the voltage down to the resting state. Actually, it overshoots it, and then it goes back to the resting state. Okay, so that was the basic dynamics. And we want to do is to study this model. Okay, and what we're going to do is that in this model, we put this term here, which is the applied current. And actually what we are going to do is we are going to inject different types of applied currents and see what is the response that we obtain for this system, okay? Which is actually the response that the neuron also does in experiments. So the first thing is we're gonna inject an applied current, which consists of a step function like this, okay? And we are gonna, and what's gonna happen is that when the strength of this input is weak, okay, like for instance, in this case, basically the voltage displaces away from the resting state, but then rapidly relaxes back to the resting state, because the underlying system, the system has an equilibrium point which is stable. So we perturb it a little bit, and the trajectory goes back to the attracting equilibrium point. What happens now if this we increase the strength of this applied current? What happens now is that the system also goes back to the resting state, but before it performs a long excursion along in the phase space, and we have this huge change in the voltage, rapid change in the voltage, which is actually the action potential, before it relaxes back to the resting state, to the equilibrium point. These systems that they have this property, that they can show these large excursions of the trajectory, are called excitable systems. And the models for a single cell, for neurons, are excitable systems, okay? Let's see what happens if instead of applying a step current, we apply a current and we keep it constant. So we keep it, so we don't bring it back to zero, but we keep this constant. We keep applying this current. What happens And now let's increase the strength of the input, okay? So if this is slow, what happens is that the system has this stable equilibrium, and basically it does this rapid, it does this long excursion, the action potential, and then relaxes back to the equilibrium. And it remains there. But if we increase the value of the strength of the input, so if we increase the amplitude of the applied current, what happens is that now these action potentials keep appearing. So they keep repeating over and over. So what happens here is that the system has undergone a transition, actually a bifurcation. And what happens is that now there is an invariant object in the system, which is stable and is a periodic orbit. So we've gone from having a stable equilibrium point to having a stable periodic orbit. So the system has undergone a bifurcation. And this is what I want to talk about today in today's lecture in more detail. Actually, if we keep increasing the value of I applied, we still see that we have this periodic orbit, this repeating rhythm in the voltage. And actually what happens is that the frequency increases with the value of the applied current. Until, if this value is too strong, what happens is that what the system has now is again an equilibrium point which is stable, which is now it's not corresponding to the resting state, but is it a high voltage state? And actually, in these high voltage values, what happens is that the cell is not excitable anymore here. Okay. Sometimes this is called the oscillator's death. Okay. So this is what I want to talk about today, is that the type of bifurcations that we observe in these systems. I'm going to show you now the bifurcation diagram for the Hudson-Huxley equation. Sorry, I was reading what was in the chat, but I think it's not a question for me. So I'm going to show you now what is the bifurcation diagram for the Hudson-Huxley model. This might be for experts in dynamical systems. So if you are not familiar with it, don't worry, because I'm going to explain you this in detail for today's talk. But I want to show you here that what happens is that when we vary the parameter I applied, what happens is that we first have a stable equilibrium point for which we are showing the corresponding voltage coordinate. And then at a certain value of the applied current, what happens is that this equilibrium point becomes unstable, okay, which is indicated here with the dashed line, until at a certain another value of I applied, it becomes stable again. So we have transition from having here in this region is where we have this stable resting state. And then at some point this becomes unstable, and then we go to this high value, to this other equilibrium point for which the cell is at a higher voltage value, okay? In the middle, what happens here, this transition from in the stability of the equilibrium point occurs via a Hopf bifurcation, a subcritical Hopf bifurcation. And actually what happens is that there is an unstable periodic orbit that dies in this bifurcation. This dashed line shows, okay, these values here show the maximum and the minimum, values of the voltage along this periodic orbit, okay? And apart from this, what we have is that there is another periodic orbit which is stable, for which here we are showing the maximum and the minimum, okay? that this stable periodic orbit is born out of a saddle node of limit cycles, okay, and then dies here at the half bifurcation, second half bifurcation. So what I'm saying here maybe is something well known for people in dynamical systems, but if you're not familiar with this, don't worry, because this is what I want to explain in more detail today, okay? So let's see how we study this. But first, let me motivate a little bit the topic of excitability for neurons. In 1948, Hudson, which is the same as Hodgkin, who is the same scientist in the Hodgkin-Huxley model, studying experimentally the responses of excitable membranes when he was injecting steady currents, and looking at what is the response of these membranes. And he identified two types of different responses in the cell membranes that he classified as class 1 and class 2. For class 1, he observed that as he was injecting these steady currents, at the beginning, he only had the action potential and then going back to the resting state, as you can see here. But then when he was increasing the strength of the applied current, the neuron started to show oscillations. And when this, the membranes he was recording started to show oscillations, they did it at a very low frequency. So he was injecting current, okay, of different intensities. And for low values, he didn't have any periodic response. But when the cell started to show repetitively action potentials, they started with a very low frequency, very close to 0. And then as the current intensity increased, the frequency increased, okay? However, there was another type of cell membranes that he called class 2, that similarly, for low values of the input current, they didn't show any oscillatory behavior. It was just an action potential and then back to the resting state, as you can see here. But then there was a value of the current intensity for which these cells started to show oscillatory behavior, but they started with a positive frequency that could not bring back to 0, okay? And another property that observed is that these cells here, the class 1, when they showed just this this excitability property, they had a long latency before having spike, while this was much faster. He also identified another class that I just mentioned here, which is class 3, which were cells that they never showed oscillatory behavior. So they always, after a transient period of having like 1 or 2 spikes, they relax it back to the equilibrium, okay? So this was, this classification that I summarize here was basically based on experimental data, okay? Just saying, okay, type 1 or class 1, they had sharp thresholds, they had excitability with long latency, and firing at arbitrarily low frequencies. While type 2 showed variable thresholds, don't worry about this, excitability with short latency, so the spike was appearing like very soon after the injection of the current, and a positive minimal frequency for firing. So when they started to show oscillations, they did it with a positive minimal frequency. And then there is this class 3 that basically the main feature is that they failed to repeat, okay? And what I want to tell you about is what is the mathematical formulation that is behind these two excitability classes. Okay. This was proposed by Rinzel and Ermentrout in '89, and will help you. I think it's a nice work to look at, because it also helps us to review some concepts of dynamical systems. We're going to see that each of these types is linked to a particular bifurcation. So to do that, what we're going to do is we are going to reduce our, remember that the Hodgkin-Huxley model that I presented is 4-dimensional. So what we're going to do is study models in 2 dimensions, okay, on the plane, because it will be easy for us to show some properties. So the Hodgkin-Huxley model can be reduced, which is 4-dimensional, can be reduced to 2 dimensions using the following tricks. The first one is that remember that it has 3 gating variables, but one of these gating variables is really fast. It has a very, the time constant is really small. So what we can assume is that M activates so fast that we set it equal to its steady state value. Okay. So as this is like thinking is that is like if the time constant is 0. Okay. So things go very fast. And another important feature is that if we look at the evolution of the variables n and h, which are the other 2 variables, 2 other gating variables in the model, there is a linear relationship between these 2, which is approximately given by this expression here. So what does it mean? That if we know the value of n, we can obtain the value of h basically using this linear relationship. This allows us to eliminate one of the 2 equations. So in this particular case, we have eliminated the equation for h and just replaced h by this expression here in the Hodgkin-Huxley model, while we have replaced m by its steady state value here. And what we have is just now a 2-dimensional model with the variable voltage and the variable the gating variable n, which controls the opening of the potassium current. Okay. So here I'm showing this picture simulations of the original Hodgkin-Huxley model for dimensions and the reduced Hodgkin-Huxley model that I just presented here, which is 2-dimensional. As you can see, of course, it's not exact, but for the purposes of this study, it's good for us. Okay. So there are other 2-dimensional models that are also very well known and that I'd like to mention here. Okay. One is the Morris-Lecard model, which is a model designed by Morris and Lecard for the giant, to describe the membrane voltage for the giant muscle fiber of the barnacle. Okay. And this again is a 2-dimensional model that involves the voltage, the variable voltage, and a gating variable, in this case is W. But as you can see, it has the same shape as the reduced Hodgkin-Huxley model. Here it has this term here, which is the ionic current corresponding, in this case, to calcium, but calcium plays the same role as sodium, okay? Which is like when these channels open, basically it depolarizes the cell. It causes the voltage to rise. And on the other hand, we have this ionic current, the potassium, which is the responsible of repolarizing, and for which we include this gating variable, W, that has these dynamics. And the dynamics is also, for this gating variable, is expressed by this typical equation for the dynamics of a gating variable that I discussed also in the previous section. Okay, and this model has been extensively studied. It's very classical because, as you can see here, there are several parameters that you need to choose. So for instance, the calcium conductance, the potassium conductance, the reversal potentials, these leak terms. Okay, all these are parameters also here in these equations. There are parameters that need to be chosen. And this has been classically studied because depending on, there are like two sets of parameters that they give rise to two different types of bifurcations in this model. And this is what I want to explain you, okay? Because I'm gonna show you the responses that Hodgkin observed in his experiments that can be reproduced with this model, choosing appropriate parameters, okay? There's also another model, two-dimensional model that I want to comment, but just because it's a classical model and on a course on mathematical neuroscience, I felt that I had to mention it because it's very classical. It's the Fitchuk-Nagumo equation, which is a simpler model of excitability because this is a model for an excitable system. But as you can see, in this case, it doesn't have the membrane biophysics in the sense that here we don't have the ionic currents and expressed, yeah, we don't have an expression here of the ionic current. This is basically, as you can see, it's a polynomial. These are polynomial functions. And the nice thing of this is that it simplifies a lot the expression, and it can reproduce the same type of properties. Okay, and because of that advantage, it has been used a lot in mathematical neuroscience, but also in other areas of where there appear excitable systems. Also, people in dynamical systems have studied this model a lot. Okay, especially also the PDE version where we have diffusion. Okay, this was just an aside comment. So we go back to the Maurice-Lecar model. And to study, so this is a two-dimensional model. So to study these models in dynamical systems, what it can be useful is to identify first the null lines. Okay, so these are models that have this form. So we have an equation for the voltage and an equation for a gating variable that we're going to call W. And we're going to identify on the phase plane, we're going to identify the null lines. These are the set of points on the phase space where the velocities of these variables vanish. Okay, typically in the neuron models, the V null line, this function that I wrote as f, it has is a cubic function. So when we plot it on the VW phase plane, this typically the V null line looks like a cubic function. So this is V dot equal to 0, while the W null line actually is a sigmoidal function. Actually, remember that this is usually W infinity of V minus W divided by tau infinity of V. And actually, when we set this equal to 0, what we have is that W is equal to W infinity of V. And this I discussed on Tuesday, that this is a sigmoidal function. So it's a function that looks like this. Okay, so it goes from 0 to 1. The places where these null lines intersect correspond to equilibrium points of the system, because in these places, both the velocities of both variables vanish. Okay, and so these are the equilibrium points. And then there is another interesting aspect of these systems, which is that typically they have a slow-fast dynamics. What is this? And this is usually represented with the parameter epsilon in front of the function, in front of the function defining the rate change for the gating variable. Is that usually the voltage variable is much faster than the gating variable here. Okay, so this means that if we go back to the node line drawing, okay, so if this is V and this is W, so away from the V node line, okay, so of course on the V node line the velocity of V is 0, and then this is different. But away from the V node line, what happens is that the vector field is, in this case, it will be horizontal in the sense that the direction is going to be towards like this. And here also I'm using that I know already what is the direction. We should see that on this part of the phase plane, B dot is positive, while here B dot is negative, etc. So here I'm using a lot of information that I already have. Okay, but the vector field looks like this. And actually, except when we are on V dot equal to 0, which this is called typically in the context of slow-fast systems, is the slow manifold. And here it is dominated by the dynamics of W. Okay, and actually what happens is that for the trajectories, let me change the color. I want. Sorry, I want to change the color, but I don't know how to do it. Anyway, so let's see what happens with that trajectory. So this is the equilibrium point. If we do a brief perturbation and we increase the voltage a little bit here, oops. And we increase the voltage a little bit and we move up here, what happens is that the dynamics brings us back to the equilibrium point. But if we increase the voltage by a higher value, for instance, and we lie in this region here, what happens is that the dynamics pushes us towards this direction until we reach this slow manifold, and then the trajectory slides down along the slow manifold until it reaches this right knee, and then the vector field, again, the dynamics pushes us back here, and then the trajectory relaxes back to the equilibrium. So this trajectory that I've shown, notice that corresponds to a rapid increase in the voltage, because this is in the direction of the voltage, followed by this active state here while we stay on this right branch, and then followed by a rapid decrease in the voltage. So this corresponds. So this is time and this is voltage. This corresponds to this slow and then back to the equilibrium. Okay. So this is what happens when the equilibrium point is stable. When the equilibrium point becomes unstable, so here I think I put a plot. So this is what happens when the equilibrium point is stable. This is the intersection of two node lines. We have this fast dynamics that pushes us here, and then we move slowly along the slow manifold and then back to the resting state. But if this equilibrium point now is unstable, what happens is what emerges here is a periodic orbit that has also this shape like this. We go fast from this left branch of the stable of the slow manifold, Then we move along this right branch of the binocline or the slow manifold, then also a rapid change here, and then again moving slowly along this branch, and then jumping up again. What we have here is this oscillatory behavior. Okay, I'm exaggerating. And these oscillations where you have like periods of rapid changes followed by this slow evolution of the slow variable are called relaxation oscillators. Okay, and this is also a big field in dynamical system theory where there's a vast literature, and it's something there are like very interesting problems and to explore. But actually, so this has many applications in neuroscience, because in neuroscience, what we have is excitable systems that then when they transition to, when we have transition from an equilibrium state to a periodic orbit, the periodic orbit that appears is a relaxation oscillator. Okay. Again, just saying that to determine, so with the null lines, we could see that where the both null lines intersect is where we have the equilibrium point. But then if we want to know the stability of this equilibrium, basically what we need to know is we need to compute the Jacobian matrix, evaluate it at the equilibrium point, and then look at the eigenvalues of this Jacobian matrix. If in this case we are in 2 dimensions, so if both eigenvalues have a real part which is negative, we say that the equilibrium is stable, while if one of them is positive, the equilibrium is unstable. And we say that for those values, when the real part is equal to 0, there occurs a bifurcation. Okay, if a parameter. So let's say that we have an external parameter, we have an equilibrium which is stable because the real part of its eigenvalues is negative, and then at some point, for this value of I applied, the equilibrium point has an eigenvalue with real part equal to 0. We say that here a bifurcation occurs. Okay, and essentially, this is a little bit of a summary of what we can have on the plane, is that based on the trace and the determinant of the Jacobian matrix. So here this is the determinant, this is the trace. So for negative values of the determinant, what we have is that the eigenvalues are always real, and one is positive and the other one is negative. So the type of equilibrium point is a saddle. While for values of the determinant which are positive, okay, then we can have for positive traces, and then also it's important this curve. What we have is that for positive traces, the equilibrium point is unstable, but above this curve, it's a node. So the dynamics nearby looks like this, while for values above this curve is a focus. So the trajectories around this equilibrium point spiral around. So they move away from the equilibrium, but they spiral around it. And the same happens for negative values of the trace, but in this case, the equilibrium point is stable. So it attracts trajectories nearby. Okay. So this is just a comment so that we can follow what is coming next. So let's go back to our Morris-Lecard model. And let's choose a particular set of parameters that I didn't write it here, but so that when we simulate this system and we compute the solutions, what we obtain is or when we study this system, what we obtain is the following. Here is going to be important the parameter I. Okay, this parameter I here. This is the parameter that we are going to vary. Okay, and we are going to see if there is any qualitative change in the dynamics when we vary this parameter. So for low values of the parameter I applied, what I'm showing here in picture number 8, this is these are the knot lines again. Notice the cubic knot line and the sigmoidal knot line. So they intersect at this point, and this point is stable, okay? And is actually it's a stable focus. And here what I'm showing is like 2 trajectories that they reproduce the dynamics that I just explained you before. Trajectories that start nearby this equilibrium relax back to the equilibrium rapidly, like you can see here, while trajectories that start a little bit far away with a higher value of the voltage, they do this long excursion before returning to the resting state. So we have this shape here for the voltage. Now, if we increase the input a little bit more, the value of the applied current a little bit more, what we observe is that the system has the equilibrium point where the both knot lines intersect, which is still stable. Okay, it's stable. But then there appears an unstable limit cycle here. Okay, and then a stable limit cycle here outside. So we have these 3 invariant objects: the equilibrium point, which is stable, the unstable limit cycle, and a stable limit cycle outside surrounding them. And actually the trajectories, they do like this. In this situation, the system is bistable, because if we start inside the unstable limit cycle, the trajectories approach the equilibrium point. While if we start outside of the unstable limit cycles, the trajectories approach the stable limit cycle. So depending on where we put the initial condition, we end up, or the trajectory tends to a different attractor. Okay, and we say that in this situation, the system is bistable. If we keep increasing the current, the I applied current a little bit more, what happens is that now this unstable limit cycle has shrunk and collapsed at the equilibrium point. And at this moment, the equilibrium point has become stable. So now the equilibrium, sorry, has become unstable. So now the equilibrium point is unstable. So the trajectories nearby move away from it. And what we still have is the stable periodic orbit outside. Okay, so if we start with a trajectory, this trajectory moves away from the equilibrium point and approaches the stable periodic orbit that is outside. Okay. Here there have been several bifurcations, and since well, I don't have much time, but let me comment briefly. So there's been, so let me tell you about the Hopf bifurcation. So the Hopf bifurcation occurs when we have stable a focus, an equilibrium point, which is a focus, and then it changes the stability, this focus. So we go from a stable focus to an unstable one, or vice versa. Okay. When this happens, at this point, we say that a Hopf bifurcation has occurred. Okay. And there are 2 types of bifurcation, Hopf bifurcations: the supercritical and the subcritical. The supercritical, that has this normal form in polar coordinates given by this expression here. Okay, where here the parameter that for which the system undergoes a bifurcation is the parameter mu. Okay, and what you can see is that by looking at this function of R, okay, is that if let me say here, if mu is negative, this function, if this is R and this is f of R, this function f of R looks like this. So it intersects, so this is equal to 0. So this intersects the x-axis only at one point, which is the origin and which is the equilibrium, okay? And actually this equilibrium is stable. It attracts trajectories nearby. So for mu equal to 0, exactly equal to 0, this function f of r is the same, it has a tangency here. So there is only one equilibrium, which is stable. But for mu greater than 0, the function looks like this, f of r. Okay, so it has two values where it vanishes, which correspond to r equal to 0, which is the equilibrium that we had, and the other one corresponds to r equal to square root of mu. So this is a periodic orbit of size square root of mu. Okay, so what means is that, and actually if we look at the dynamics nearby, here this is positive, so the trajectories or the dynamics is like this. So the origin now is repelling, so this is unstable now, the origin, and this periodic orbit that appears here is attracting or is stable. Okay, so what happens at this bifurcation equilibrium, when it changes stability, a periodic orbit is born of size the square root of mu. Okay, so this is a little bit of a summary. For mu smaller than 0, what we have is just an equilibrium, which is stable, and it's a focus and it attracts trajectories nearby. And for mu greater than 0, what happens is that there appears a periodic orbit, and the equilibrium point changes stability, and now it becomes unstable, and trajectories approach the periodic orbit. Okay, that's the supercritical half. Then we have the subcritical half, which is the same idea. And this is, oh, sorry, before moving to the subcritical half, this is how the bifurcation diagram looks like this for a supercritical half. So we have that for mu smaller than 0, we have an equilibrium, which is stable. And then after for mu positive, the equilibrium becomes unstable. And what is born here is a periodic orbit. Okay, this is the radius of the periodic orbit that is born out of this equilibrium, and it grows as we increase the value of the parameter. Okay, so similarly, this is just saying that, okay, the limit cycle has amplitude the square root of mu, and on the other hand, the frequency of the limit cycle is approximately given, or is given when this limit cycle is born, by the imaginary part of the eigenvalue of the eigenvalues of the Jacobian matrix at the origin. So when this limit cycle that appears, which is a periodic orbit with a frequency given by the imaginary part of the eigenvalues. So it is born with a positive frequency. Okay. Second, the subcritical half is the same idea. Okay, if we repeat the same exercise and we look at this function f of r and we look at zeros of this function, what we have in this case, notice that the only difference is that with respect to the previous system is this sign here. What we have is that for mu negative, in this case, the system has an equilibrium point, which is attracting, and then an unstable periodic orbit. Okay. So trajectories move away from the equilibrium periodic orbit towards the equilibrium point. And at mu equal to 0, what happens is that the stability of the equilibrium point changes, so it becomes unstable. And on the other hand, the unstable periodic orbit shrinks, collapses to the equilibrium, and disappears. Okay, that's the subcritical half. And in these systems, what happens is another bifurcation, which is like, well, this is the bifurcation diagram. We have the unstable periodic orbit of size the square root of mu, okay, that and the stable spiral. And as we move the values of the parameter, this unstable periodic orbit collapses around the equilibrium and disappears. And what we have in these systems actually is that before this actually in the system that I just explained you, in the Morris-Lekar system that I just explained you, I showed you that it had an unstable periodic orbit surrounding the equilibrium. But outside of the unstable periodic orbit, there was a stable periodic orbit. So actually what we have is a subcritical half bifurcation, and previously there's been a saddle node of limit cycles. What is this? Well, if you take the same system as before for the subcritical half, and we add this term here that I marked in red, and actually you do the exercise of looking at this, the zeros of this function f of r, okay? What we're gonna see is the following, is that for mu equal to 0, we are gonna have the half bifurcation that I just discussed. But before, there's going to be a value of the parameter that I'm going to call mu critical, okay, for which? For values of mu smaller than this mu critical, okay, and this is smaller than 0. What happens is that this function f of r intersects the x-axis only at the origin, at the equilibrium, and this equilibrium is stable, okay? Then at the critical value mu, what happens is that there appears here another zero of this function r dot. And at this point we have here, there appears a limit cycle, okay? At this, there appears this limit cycle. The equilibrium is still stable, it doesn't change. And there appears this limit cycle. And if we increase the values of mu away from this mu critical, what happens is that out of this limit cycle, there bifurcate two limit cycles. One that is stable and corresponds to this value of r, and is the one outside, and another one that is unstable and is inside. Okay. So here what happens, there has been what it's called a saddle node of limit cycles. So these are two limit cycles, one stable and one unstable, that they evolve, they get close together, they coalesce, they collide and disappear. If we look in this direction. In the other direction, they appear out of one and then there appear two, okay? And then this is what happens if we keep increasing mu. At mu equal to 0, what happens is that this unstable limit cycle collapses to the equilibrium and the equilibrium changes the stability. And this is the subcritical half. So we have a saddle node of limit cycles followed by this change in the stability of the equilibrium. And this is bifurcation is represented in this bifurcation diagram. So we have the equilibrium point, which is stable until mu equal to 0. But before, what we had is here at this mu critical is the emergence of a stable limit cycle and an unstable one. And the evolution of this unstable one is to get closer and closer around the equilibrium, coalesce, collapse to the equilibrium, and then at mu equal to 0, the equilibrium changes in stability and becomes unstable, okay? And in this region here, between mu critical and mu equal to 0, what we have is bistability between the periodic orbit, the stable limit cycle, and the equilibrium point, okay? So going back to what I showed, this is the type of bifurcation diagram that we have for this Morris-Lekar model. So that the resting state becomes unstable, and when it becomes unstable, the only invariant object, stable invariant object that remains is a periodic orbit. This periodic orbit is born out of this is a periodic orbit that has a positive frequency of oscillation when it's born. So this is related to the class 2 that Hodgkin studied experimentally. And now, since I have very little time, but let me comment on the class 1. So if we take the same Morris-Lekar model and we pick another set of parameters, we observe the following. We observe that for values of I applied that are small, okay, we have, in this case, the null lines intersect at 3 points. one here, one here, and one here. This is a saddle point. And this is a stable node. Okay. And then, do I have, how much time can I take?
You can, 1 second. You can still have 10 minutes, 10 minutes, 10, 15 minutes.
Yes, 5 minutes, it will be okay. Just,
I guess.
okay, thank you. In this case, so this is different what we've seen before. Before we have seen that the system had only one equilibrium point. In this case, it has 3 equilibrium points. One that is a stable node, another one that is a saddle, and a higher one here. Okay, so for low values of the amplitude, basically what happens is that the trajectories, again, these systems are slow fast. So if I'm this, if I start in this part of the phase plane, the trajectory brings me towards the null line, and then it jumps up and it relaxes back to the steady state. And we have the typical action potential and back to the resting state. But then as we increase the value of I applied, what happens now is that the saddle and the node that I had here, they get closer and closer and then coalesce here. And then if I increase the I applied even more, disappear. So we don't have any more an intersection. There is the intersection of the null lines. We don't have it anymore here. And they intersect only at this equilibrium point. But then when this happens, when we have this saddle node bifurcation, which is a saddle and a node that get closer and closer, coalesce and disappear, what happens is that out of this, there is a stable limit cycle that is born. Actually, we don't have this intersection anymore, but what we have here is a periodic orbit, a typical relaxation oscillator. A periodic orbit. Okay, so we have periodic orbit. And if we increase the value of I applied even more, and here there is an unstable equilibrium, but we don't care about these trajectories, just move away from it. Okay, and approach the stable periodic orbit. Okay, how is the stable periodic orbit that appears here? Well, this is how the bifurcation diagram looks like in these cases. So for low values of I apply, so we see here that we have 3 equilibrium points. One here, which is the saddle and is unstable, and another one up here. And then as we increase I apply, there is a moment where this saddle and the node coalesce. And then after that, they are not there anymore. They disappear. And what happens here is that there emerges a limit cycle, which is plotted by these green dots, which correspond to the maximum and the minimum of the limit cycle. So the type of bifurcation that produces the limit cycle is what is called a saddle node on an invariant circle bifurcation. Okay, and with this is going to be the last part. So typically, we know like what happens when we have a saddle and a node that coalesce and disappear. But in these systems, what happens is that before the bifurcation, the unstable manifold of the saddle enters into the, as time goes to infinity, tends to the node. And the same here for the other branch of the unstable manifold of the saddle. In the sense that we have here this orbit made of heteroclinic pieces, that is orbits that connect to equilibrium points. So we have this orbit, and then what happens is that at the moment that there is the bifurcation, that is the saddle and the node coalesce, what happens in this moment is that the unstable manifold of the saddle, we have this homoclinic orbit, enters here. And after that, the saddle and the node disappear, but what remains is this limit cycle, which inherits the dynamics of this homoclinic orbit, in the sense that the homoclinic orbit is a trajectory that as time goes to minus infinity and plus infinity tends to the equilibrium. So you can think as if it is an orbit within infinite periods. So when the orbit that appears here, it appears, it inherits this dynamic. So it appears with infinite period or very large period. In other words, with a frequency that is very close to zero. Okay, so this is associated to the other Hodgkin halves. Okay, so as a summary, we have that the oscillations that Hodgkin called +1 and that he observed that they appeared with a fixed frequency, with a positive frequency, sorry, are associated to a half bifurcation. While the cells that responded with an excitability property such that when the oscillations appear, they do it with a very low frequency, are oscillated to a mathematical model that shows a saddle node on invariant circle bifurcation. Okay, and that's the relationship between mathematical bifurcations and experimental studies. And with this, I finish because I took a little bit more. Sorry about this.
No, it was great. Thank you. Thank you very much. Very nice indeed. So, question? See? No, say, yes?
I see that there is a question here in the chat that says, if you compare the two-dimensional version with respect to the four-dimensional one, what types of behavior are missed in the lower dimensional model? Well, what happens is that since as I explained, basically the dynamics in the four-dimensional model, there is the dynamics for M, which is very fast. So it pushes the trajectories in that direction, very soon are pushed towards the steady state of the M value. And on the other hand, there is this linear relationship between the variables, the other two variables. So this is, in some sense, is like in the four-dimensional model, we can find a two-dimensional invariant subspace where we study the dynamics. And actually what we can see is that the dynamics for the four-dimensional model is pushed towards this. And this is what we study with the two-dimensional models. So in this sense, qualitatively, we are not losing information. We are losing information in terms of not losing information. So quantitatively, obviously, they give different results. As I showed you, the shape, for instance, of the action potential was a little bit different. So there are these quantitative differences.